In this video, I'd like to talk about the math question of the day for Thursday, July 20th, 2023. And with this problem, we need to consider this polynomial function, h of x, which is a fifth degree polynomial. And we're asked, what is the end behavior of the graph of this function h? So a question like this is typically seen in an Algebra 2 class. And at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start going through it. And the end behavior of a polynomial is referring to what happens as the x value gets really, really big or approaches infinity, and what happens to the x value as we approach negative infinity. It gets very large, but in the negative direction. So how does this polynomial function actually behave at those large or very negative x values? And the end behavior is dominated by whatever the highest power term is for your polynomial. As x gets bigger and bigger or more and more negative, these lower power terms matter less and less. And you can imagine if you plug in a very large value of x, let's say x is 1,000,000, which we can write as 10 to the 6th, we can evaluate our function by plugging in 1,000,000 here, and we would get minus 2 multiplied by 10 to the 6th to the 5th power, which would really be 10 to the 30th power. Then we get plus 8 times by 10 to the 6th to the 4th, which is 10 to the 24th power, minus 2, and if we square this, we get 10 to the 12th, and then we have plus 15 here. So what we can notice by plugging in this very large number, and we could plug in much larger numbers, is that these lower power terms will not really affect this highest power term here. Since we can notice that this number has 6 more zeros after it than this number. So in some sense, it's like taking negative 2,000,000 and then adding 8 to it. The number will still basically be negative 2,000,000. The plus 8 will barely change it. Though, of course, we're dealing with much larger numbers, but that is the difference between this. Since this has 6 zeros more, it is 1,000,000 times greater, at least when looking at these factors here, not including the coefficients. It would be 1,000,000 times greater when looking at this number here. And it's even worse with these lower power terms. These will barely change the number at all. And the bigger that x gets, the more dominant this leading term becomes. So with the end behavior of a polynomial function, we really only care about the highest power term. And that will determine the shape of the graph. But in this case, our highest power term is minus 2 times by x to the 5th. So we need to understand how does a fifth degree polynomial actually behave as x gets bigger and bigger or more and more negative, and then what happens when we multiply it by a negative number. So to understand that, we need to consider the different parent functions. For instance, if we have the function, let me actually make some space here, and we can look through them all. Let's say we have the function y is equal to x squared, and let me draw in a quick coordinate plane here. If we graph this, this is just the parabola. We can see that as x gets bigger and bigger, it shoots off to positive infinity, and as x gets more negative, it shoots off to positive infinity. And you can test this by just plugging in values. Positive values will just get bigger and bigger, and negative values, when you square them, will become positive, and they will also get bigger and bigger as you put in bigger and bigger negative values. Now, if we look at y is equal to x to the 3rd power, now on the positive half of the coordinate plane for x values, it will approach infinity even faster than the parabola. But on the negative side, now when we put in a negative number and we cube it, we get back a negative number since only 2 of those pair up. So this will actually decrease and go down to negative infinity. And likewise, if we look at y equals x to the 4th, this is very similar to the parabola, but will approach infinity much faster. Since in both cases, when you put in positive or negative numbers, your result will be a positive number. And lastly, since we need to know about fifth degree polynomials, this will behave just like the cubic polynomial here, where when we put in positive numbers, it will grow faster than all the previous ones, since now we're raising it to the fifth power. But for negative numbers, 4 of those numbers will pair up and cancel out and become positive, but then we'll have a fifth number that is negative, and negative times positive is negative. So whenever they're to an odd power and we put in negative numbers, our output will be negative. So this will also decrease or go towards negative infinity as x gets more and more negative. And just to complete this, these are the x values and these are the y values. This is the positive side, and of course this is our negative side here. So what we can learn from this is that our function will behave like this pink curve here, but we are also multiplying it by a negative number. And in all of these cases, when you multiply by a negative, you switch the y values from being what they currently are to their opposite. So if we look at, let's say, y is equal to minus x squared, we're looking at this white parabola here. All of the y values will now reflect across this x-axis, and we'll end up with a parabola that is downward facing. As x gets bigger and bigger or more and more negative, the function will approach negative infinity. And of course, with all of these, you can test it out by just plugging in bigger values or more negative values. So the one we're concerned about with is the pink curve here. And if we were to put a negative sign in front of it, and it could also be minus 2 times by x to the fifth, but the coefficient itself will just scale it. It will make it either move faster towards infinity, or if it's multiplied by a fraction, it will widen it out a bit. So the coefficient doesn't really matter. That just determines the speed at which it will go to positive or negative infinity, but the negative sign will cause a reflection. And since we're looking at this pink curve here, the y values will be the opposite. So on the positive half of the plane, these reflect downward, maybe less steep than that, so probably something like that. And on the negative half of the plane, in terms of the x values, the y values were negative, but now they will be positive. So it'll look something like that. Let me try to redraw that a little bit neater. So what we can take away from this is that our polynomial function h of x is going to behave just like this fifth degree polynomial that's multiplied by -1. And what we can see is that as x approaches infinity for this curve right here, the y value, notice, approaches negative infinity. It is getting more and more negative. But if we look at as x goes to negative infinity, now we're looking at the left half, the y values get bigger and bigger. So y would approach positive infinity. And like I said, since for our polynomial function, this is dominated by this highest power term where we have a -2 times x to the fifth, the end behavior of this will react the exact same way as the end behavior of this equation here. So while this is true for this equation, y is equal to minus x to the fifth, it is also true for h of x. So we can say that as x goes to infinity, h of x approaches negative infinity, and as x goes to negative infinity, h of x approaches positive infinity. And like I said, by putting a 2 in front of it, all it does is scale it. It will make it steeper. So now we would have the curve just closer to the y-axis, essentially. So it might look something like that for its highest power term. So the coefficient in front just changes the steepness, but doesn't actually change the orientation and how it approaches positive or negative infinity. Now, I should mention that these lower power terms do have an effect for smaller x values and will basically cause the function to wiggle or move around. So it probably won't be at the origin, it will be shifted around somewhere, and then it will move up and down. So we could check this on a graphing calculator. In fact, that's probably the best option to check your work. I'll leave that as an exercise to the viewer. You can use Desmos, but you might see some type of function that looks maybe like that. And it could be shifted somewhere on the coordinate plane. It's hard to say without actually graphing it. But this will give you some idea of what this polynomial function might actually look like.